Hello all. We have reached the end of Unit 4 after many lessons, and we have this review sheet here. I'm going to fill it in for you. Please copy notes as you go. And if I remember, perhaps you can remind me, if anybody watches this video a couple days early, to make you a copy of this review sheet because it could make your notes taking quite a bit easier. But if I do forget to make you a copy, just you're going to be writing a lot. Okay, there is a quiz associated with this lesson, so be ready for that. And let's begin. So my first section to discuss is bonding, and we're going to state the changes that occur in each of the following when bonds form, what happens to potential energy, and what happens to stability. So potential energy actually decreases when bonds form, and stability increases. But when bonds break, as in section B here, potential energy increases while stability decreases. On to bonds. We have our ionic bonds, we have our covalent bonds, and of course we have our metallic bonds, which I believe are on the next page. So the definition of an ionic bond is the transfer of electrons between a metal atom and a nonmetal atom. A good example could be between any metal and nonmetal. For some reason, I'm thinking about sodium and bromine right now. Sodium would give its only electron to bromine as it would transfer. So bromine has 7 at the moment, and it would accept 1 from sodium, and that would be the beginning of your ionic bond. I'll follow with the dot structure that each would have as a result. For metals, brackets, no electrons, positive charge. For the non-metal, brackets and 8 electrons with a negative charge. The degree of ionic character can be determined by calculating an electronegativity difference. The largest electronegativity difference will give you the most ionic character. And the properties of ionically bonded substances are several. I'll write them down. So I have high melting point, high boiling point, brittle, hard, and they conduct when liquid and or melted, liquid or dissolved. And you might see parentheses L and parentheses AQ, L for liquid and AQ is aqueous, which means dissolved in water. The definition for a covalent bond is when 2 nonmetal atoms share electrons. Another name for a covalently bonded substance is a molecule. And the properties of covalently bonded substances are essentially the opposite of what I've written above for ionically bonded substances. So on to polar covalent bonds. The definition is a covalent bond with unequal sharing of electrons, which is a result of a difference in electronegativity between the atoms involved in the bond. The example that comes to mind right now would be hydrogen fluoride. They will share, each atom will share 1 electron to create 1 pair of electrons or 1 bond, but the fluorine side is more electronegative than the hydrogen side, and therefore that difference in electronegativities is going to make the electron cloud quite a bit larger around the fluorine side of the molecule. A person would determine the degree of polarity of that bond by determining an electronegativity difference, just the same way that they would determine the degree of ionic character with an electronegativity difference. Nonpolar covalent bonds would be between 2 nonmetals of the same element, and the reason is because those 2 nonmetal elements would have the same electronegativity. I can think of at least 7 good examples, and those would be all of the heavenly 7. So we have H2, N2, O2, F2, Cl2, Br2, and I2. Okay, lastly, metallic bonds. Metallic bonds occur between atoms of two metals. And of course, the term that's associated with them the most closely would be the mobile sea of electrons. I did highlight that basically anytime you write the symbol for any element, you are implying that it has metallic bonds. And the reason is because when I write the symbol of any metallic element, I'm not saying that I have one atom of that element. I am just saying that I only have one element, of which there could be gazillions of atoms, and they of course would all be metallically bonded to one another. So when you are trying to identify a metallic bond, you do not need to feel like you need to see two mercuries bonded together or two golds bonded together. Just know that if I write the symbol for only one metallic element, it will experience metallic bonding. So those are my examples that I would use here. The properties that metallically bonded substances are many. I'll write some of them down. On to molecules. So in terms of structure and or distribution of charge, a molecule would be considered polar if it has an asymmetrical structure or an unequal distribution of charge. The example I chose was that of ammonia, which has this particular asymmetrical unequal distribution of charge structure. So in contrast, a nonpolar molecule would be described as symmetrical or having an equal distribution of charge. And I chose 7 examples, or the heavenly 7, because each of these molecules would have symmetry. But I'll also choose 1 or 2 other examples, such as methane, which has symmetry and equal distribution of charge, and carbon dioxide, which also has symmetry and an equal distribution of charge. On to intermolecular forces, the definition for which is a force of attraction between molecules. An unequal distribution of charge is actually caused by differences in electronegativities between the atoms involved in the molecule. Now, hydrogen bonding is the most important example of intermolecular force that you're responsible for knowing. There are only 3 molecules which you'll commonly be expected to remember experience hydrogen bonding. And those 3 molecules are water, ammonia, and hydrofluoric acid. But if you were to look at these 4 molecules and you were asked which one would have the greatest degree of hydrogen bonding, of course you could immediately say HF because it's the only one that immediately meets the requirements for hydrogen bonding in that it has a hydrogen slightly positive end and a nitrogen, oxygen, or fluorine slightly negative end. But I also want you to point out that in other states and in other places, all 4 of these molecules would be considered as having hydrogen bonding. So what I would say that would work anywhere you are is that you would look at electronegativity differences. And HF would have the greatest degree of hydrogen bonding because it has the largest electronegativity difference. And you probably also remember that the largest electronegativity difference, or the greatest degree of hydrogen bonding, is also going to yield the highest melting point and the highest boiling point for all these 4 molecules to HF. So it'll be HF again, and it's because it has the largest degree of hydrogen bonding. I have one important note to add here, which is that even though, let's go back to these 3 molecules here. Even though of these 3 molecules, HF has the largest electronegativity difference, water actually has the largest boiling point. And the reason is because it has a large electronegativity difference, even compared to all 3, but it also has the most extensive hydrogen bonding, meaning that each of the 2 hydrogens has an opportunity to bond to a neighboring molecule. So of the molecules, the four molecules that from the previous slide, HF, HBr, HI, and HCl, the one that would have the lowest boiling point would be HI, and that's because it has the lowest electronegativity difference. So, molecule-ion attraction. Molecule-ion attraction happens when a polar molecule has an opportunity to bond to an ionic substance. And the diagram that I'll draw here is between a molecule of water, a sodium ion, and a chloride ion. So the areas that would experience attraction are in my red dotted lines, and they are happening between the negative ion and the slight positive pole of the water, and the positive ion and the slight negative pole of the water. And in my last point for intermolecular forces, please consider that fluorine, which is F2, a nonpolar molecule, is a gas at room temperature, while iodine, also a nonpolar molecule, is a solid at room temperature. And in terms of intermolecular forces, this can be explained. Basically, iodine is a large nonpolar molecule, and therefore it has dispersion forces that keep it attracted to each other and allow it to remain solid. Additionally, it's heavier than fluorine molecules, which encourages a solid form. So consider the molecule for HCl. What do the dots in this diagram represent? It would be valence electrons only. And sometimes when we draw these dot structures for certain molecules, such as N2, you'll see that you have multiple bonds between the atoms in the molecule. Each bond represents a pair of electrons. So in this particular molecule, where we have 3 bonds, you also are going to have 3 pairs of electrons, or 6 electrons. I also took a moment to add in the 2 non-bonding electrons on that nitrogen and the 2 non-bonding electrons on that one. Be aware when you're answering Regents questions whether they're asking you how many electrons are shared or how many pairs of electrons are shared. Because if it were pairs, the answer of course would be different. It would be 3 pairs. So in this portion, I would say let's draw Lewis dot structures for each of the following molecules. I will just throw them in here, and I think that you should take the time to memorize these 8 molecules, as they are the most commonly asked about. So I just popped those in, and I'll zoom in to show you some details. This is H2S with 4 non-bonding electrons. I have, let's see, F2 with a total of 12 non-bonding electrons. CO2 with a total of 8 non-bonding electrons. CH4 is noteworthy because it doesn't have any non-bonding electrons. Every electron is involved in bonding. O2 has a total of 8 non-bonding electrons. Cl2 has a total of 12. Ammonia has only 2 non-bonding electrons. And CCl4 has a total of 24 non-bonding electrons, all of which are important to make the diagram correct. Now, as a final step to your studying, I suggest going over each of your unit's quizzes. They're very representative of the exam this time around. And also, you could take a moment and re-watch key portions of certain videos, which you'll find on YouTube. Thanks for watching, and good luck on the exam tomorrow. Well, I suppose 2 days from now.